Greeting Earthlings! If you follow the channel, you know that we love all things Apollo, and that during our last visit to Steve Jurvetson's amazing space collection, we were given the opportunity to take 2 holy boxes of Apollo electronics to our lab. These are the boxes that brought you voice, data and live TV from the moon, and should be early masterpieces of microwave electronics, the blackest of black arts in analog electronics. Our spacecraft transponder is now fully up and running, and we have turned our attention to the ground part of the link. In episodes 9 and 14, we worked on an important but completely undocumented piece of Apollo ground test equipment, the Updata Link confidence test set. The Updata Link, or UDL for short, is what NASA used to send digital commands to the Apollo spacecraft. In a sense, this is the remote control box for the spacecraft. This box was used to send test commands to the spacecraft and check if they were properly received. It was made from boards that contain mysterious gray Motorola modules for which we have not found any documentation. And to make things worse, it was clearly missing bits. But that was not enough to stop Master Ken from reverse engineering its secrets. Ken figured out that the Motorola modules implemented simple logic functions before the age of the integrated circuit. He eventually teased out the schematics and functionality of each board. He even built a custom reverse engineering rig to automatically reverse engineer the wild wiring of the backplane. The first attempts at powering up the machine were of course unsuccessful, but after several repairs, the machine finally sprang to life when we added a missing clock in episode 9. It read its first commands from the tape and displayed it on its glorious edge-lit indicator. That felt like quite an achievement. We eventually got the digital part of the box working in episode 14, to the point where it would generate the correct coded subbit sequence, using 5 subbits for each data bit to guard from transmission errors. From there, the bits are handed over to an analog modem, which uses phase shift keying modulation, or PSK, to create the final signal. Unfortunately, one board was missing some mysterious key components, and this analog system did not work. So instead, we temporarily built a replacement PSK analog modulator using Keysight equipment loaned to us by ElectroRent. And in episodes 14 and 15, we could finally hear our commands being transmitted to the spacecraft. In this episode, we will complete the restoration by fixing this last part, which will lead us to X-raying some of the Motorola modules to find out what's inside, fight with LC circuits to rebuild missing filters, and replace our missing 1960s fork oscillator with brand spanking new 1970s technology. Hello, if you have been following the channel, you know that we have been making good progress in resurrecting a box that sends the commands to the Apollo modules, and the box was generating most of it except the analog coded waveforms. So what we had done, we had bypassed those 2 cards which we think are responsible for doing the PSK modulation, and one, as you can see, is missing stuff, and the other one, the only thing it has on it is this mystery module. There's one that's more mysterious than the others that I have already taken out. By sheer persistence, Ken was able to reverse engineer it. Ken was able to come up with that schematic. There is 4 kilohertz coming over here. Then there's 2 flip-flops I divided by 2, so you get 2 kilohertz and 1 kilohertz. And it turns out 2 kilohertz and 1 kilohertz is what you need to generate the phase shift key signal. The 1 kilohertz is used for reference, The 2 kilohertz is the one that you phase shift, and then you add the 2 and you get the PSK signal plus the 1 kilohertz reference. The only problem is that on the boards we only saw square waves. The square wave then goes into this amplifier and drives this transformer over here. That's the black guy. These pick up either the in phase or the out of phase signal, and then you see them coming out of here and being added to the 1 kilohertz. So the circuit seems to do the right thing, except it's doing it all with square waves, which makes no sense. There's a wire that goes over here to this missing things, which are labeled L. See, that's the 2 kilohertz, and it says 2 missing inductor on board 1. And then there is another one at the 1 kilohertz. Here is the 1 kilohertz, and it goes to missing inductors on board 1. So from the marking of the board, you would think there would be an inductor here, and there would be another inductor here. Except that's not going to do what we want, which is transform a square wave into a sine wave. And so I started to challenge Ken on what was in this circuit and know whether this is something else than a capacitor. And actually, he eventually figured out that this was actually the case, that inside a circuit was not a capacitor, but a capacitor plus a resistor. So we tried to see if the HPLCR meter could tease what value of components were in there if they were passive. And you can tell that it's not happy, it's hunting for something, so maybe not that circuit. Maybe if it's a serial circuit. It's not that happy either. So from Ken's careful bench test, which I did not film, the module reacts very much like a capacitance and a resistance in series, but the HPLCR meter is not able to figure out what's in there. So maybe it's even more complicated than that. Looks like we need to call in some reinforcement for help.
Several days later.
So today we have, well, Ken was his lab coat, so he's going to reverse engineer something. And then we have also John McMaster with his fancy X-ray machine.
This is one of the boards out of the mysterious Updata test box. And instead of integrated circuits, they've built it from these mysterious Motorola modules. And we couldn't find any documentation at all on these modules. I've been reverse engineering them, but we still have some questions about what's inside. So we think it'll be interesting on the X-ray.
Are you a professional reverse engineer person?
I would classify myself as prosumer. I would say about 2/3 of my consulting work is forward engineering and maybe about 1/3 reverse engineering. Okay. So not full-time, but kind of in that direction.
John is being quite modest here. He has quite a lab at his place, complete with wire bonding and laser probing stations, and my favorite of all cleanroom tools, the electron microscope. There is obviously some serious chip decapping happening in here, and you bet that the chips are going to be looked at very, very closely. And then you brought one of your X-ray machines?
This one right here is a wonderful little self-contained unit. I like to call it the X-ray microwave. So, just open this little door, pop, your chip or popcorn or whatever in there, press start, and boom, out comes a picture on the screen. So there's an open source software that I wrote for this, and I'm just going to do a little more detailed of a calibration. So I'll tell it to take 32 images. Should I be wearing an ESD strap?
I'm pretty sure you can put a whole panel of ESD through these and they will not care.
Yes, okay. Probably bipolar. Actually, this one we're not sure whether it's active or passive.
We don't think there's any transistors in this one.
Alright, let's see what we got.
Ooh,
So yeah, maybe we'll move it around.
So it is cordwood. You can see it's just a few components, and we want to see how it's interconnected.
We'll move it around so we get a few from this
side.
Do doing this by successive approximations.
We might want to put it at an angle
Yeah.
because we have... Oh, no, we're just seeing the pins.
Yeah, because you're looking at it straight down.
Armed with John's X-ray pictures of the module, Ken was then able to precisely reconstruct what was inside. It's all recounted in great detail on Ken's blog, of course, and I'll put a link in the doodly-doo. This picture in particular was very helpful in identifying the components. By sheer coincidence, team member Eric Schlepfer and his friend Wendell Oskey of Evil Mad Scientist fame are just publishing a book of stunning pictures showing the insides of electronic components. Here's a cap for you and an HDMI cable. I'll also link the book in the doodly-doo. So Eric could quickly match the X-rays with the picture from his book and positively identify the components. Here you have a Zener on the left and a carbon resistor on the right. The top view gave us the wiring and the slanted view some of the 3D structure. Here is Ken's reconstruction of the module. Ken then derived the exact schematics and found the values of the components by curve fitting with his experimental results. The two coupling circuits that I am interested in are at the left between pin 1 and 13 and pin 2 and 12. There is an extra small cap on the leftmost circuit, and that's likely what tripped my LCR meter. Then now that we know the square wave is AC coupled via a fairly large resistance to the mystery filter circuit, it's easy to figure out what the missing filter part is. A simple resonant LC tank circuit that is periodically excited by the square wave. Imagine a child on a swing, that would be the LC tank circuit, and something pushing it at the right moment, that would be the square wave impersonated here by the dog. The loose connection between the two is the cap and the resistor in the mystery Motorola module. You get the mental picture: square wave driven push at the input, sinusoidal movement at the output. So I have reproduced the situation we have in the circuit. I have a square wave generator, I have a cap and an 18K resistor, and that should feed my test circuit, and we're going to see what comes out, and the goal would be to transform a square wave into a sine wave. Let's do it at 2 kilohertz here. Go around 2 kilohertz. So I went out on eBay and tried to find an adjustable coil that would give me a resonance around 2K with a capacitor that wasn't extravagantly large, so that's 0.1 microfarad. And so that gives you about 60 millihenry. And I found an adjustable coil. Actually, there was a lot of 3, which came in handy. So here you go. It actually works. Yep. It's resonant. You can tell that if I go away from the resonance, weird and interesting things happen. So you can tell an oscillating circuit driven by a square wave does really weird things. But at resonance, if your input impedance is high enough so that the drive cannot win, and it's not too bad. Then I did the same thing for 1 kilohertz. Just put a bigger capacitor, so it goes with the squares. To go half of the frequency at 1 kilohertz instead of 2, you need 4 times the capacitor. So I have like a 0.47 microfarad capacitor here, and I retune my coil, and down we go. And then I had a problem. I could get my sine wave, but it's much smaller. It's less than a fourth of what I had. It's 0.4 millivolts. And the reason this happens is because coils are imperfect, and they're notoriously so. It has parasitic resistance from the wiring that starts to mask the inductance from the coil. And the way you measure that is by the Q factor, which will basically tell you how well it resonates. If it were perfect, it would resonate to infinity, but it's not. And the Q factor is the ratio of the inductance from the coil to the resistance of the wire. And unfortunately, the resistance of the wire is constant. In the case of this one, this is 90 ohms. And the inductance of the coil goes down with frequency, is 2 pi fl. So when I went down from 2 kilohertz to 1 kilohertz, my Q factor went down by a factor of 2. The other factor of 2 is that the impedance of the coil itself had gone down by a factor of 2. It went from about 600 ohms at 2 kilohertz to 300 ohms at 1 kilohertz. So I got a factor of 4, which is why my circuit was so low at 1 kilohertz, and when I put it back into the Apollo box, I couldn't get the right mix of 1 kilohertz and 2 kilohertz. So what to do when you have a coil that doesn't behave? Well, you get more coils. So I went on an expedition to my to Excess Solutions, our local recycler, and my hopes were high with this one, which was 800 millihenries, so it's more than 10 times what I used, and then the resistance was only 178 ohms. So let's try this one. And of course, since it's a bigger coil, the capacitor is much smaller. I think it's 0.33 microhenry, something like that, microfarad. And ta-da! Look at that! Tons and tons and tons of voltage. 3.3 volts. So that looked good from far, but when I went up closer, I got worried by something else. My sign is not very sinusoidal at all. So what it is that I thought the Q of that little coil of that big coil was high, but it's actually low. And it starts to dampen. When it starts to dampen, it deforms, then I kick it again and it starts to go at high speed, and then it dampens out. So I got a very strong signal, but with a large deformation due to damping, which I did not expect since the coil resistance was so low. Some of you probably guessed why already. The dampening came from the core losses. This had a laminate core, which is downright horrible when it comes to losses. So when I measured it on my HPLC-R meter, it gave me a Q factor reading of 4.3, which is catastrophic in this application. Dang, I knew this from the books, but until you hit it for real, you don't really connect it with reality. So I'll skip over all the coils to get to the winner of them, which is this guy. Look at that, 2 ohms, back in L. The Q is 90. So there's coils all over the place. It goes from Qs that are less than 2 to some that are in the hundreds. So yet another thing that's in the books but does not get real until you experience it. Since Q is proportional to frequency, it's very easy to get high Qs at high frequency and super hard to get good Qs at low frequency. It just drops like a bomb. A coil coded with a Q of 1000 at 100 kilohertz will only have a Q of 10 left at 1 kilohertz, which is why good audio coils used in speaker filters are so expensive. They use thick wire and are air-wound to eliminate loss problems, which makes them very large. And I made 2 versions of the LC circuit with that coil. So one with just 1 coil. Yoo-hoo! Here you go. And we have the 1 kilohertz coil. Whoop. For that one, I use 2 coils, so I don't get hit by the lower impedance, and I get an equally good result of 1.7 volts, and it looks like a sign. So we've got the filters now hooked up to the uplink data box under watchful eye of Ken, the master of the data box.
So yeah, the original filters were removed from this board when it was scrapped, so Mark had to rebuild the filters. These filters turn the digital square waves into nice sine waves.
Let's try to see if it works.
Okay, here we go.
And you want to explain, Ken, what we see?
So the green line is the digital data with each bit converted into 5 sub-bits. The yellow line is the phase of the sine wave changed according to the bit. So each transition you can see the phase changes.
Yeah, so that's this line here.
And this is at 2 kilohertz. It's added in with a 1 kilohertz sync signal to give us the final result in blue. And then the amplifier output is in pink.
And you can see that we got it. So the only thing that we haven't integrated in the box is the oscillator. We're still using an HP oscillator at 4 kilohertz, and it turns out it's super sensitive to the frequency because filters get detuned easily. They get out of phase actually before they get detuned. So they use a fork oscillator. Yes, you heard right. They used the most stable low frequency oscillator they had at the time, the tuning fork oscillator. And you guessed it, it uses a musical tuning fork as the resonant element. Here is a version from the tube era, and it is impressively stable. And don't you laugh at it, because they are still made today. The same miniaturized principle is used in newer MEMS oscillator devices. The resonant mechanical structure is shrunk down to a beam of micromachined silicon, but is still the exact same principle. I think I'm going to use a quartz oscillator with a divider to get to 4 kilohertz. I made one a while ago, so I'm going to dig that one out. We're almost there. I mean, this box, as far as we can tell, is sending the right signal.
Yeah, we're getting real output finally.
Yeah.
We're using 70s technology.
So this is the last touch. We added 4 kilohertz quartz oscillator because I don't have a fork. So this is a 2 megahertz and a divider. That's a board I made for driving Steve Gervais in a Soyuz clock, and ended up not using it, but it's somewhere in the divider. It has 4 kilohertz. So if I hook that one up, there we go. We have our sine waves, and we should have a box completely liberated from HP crutches. So here is the fixed up board with the 2 filters and the crystal oscillator. Note that the original board is completely unchanged. I even kept the same wires, so if we ever find the original components, we can go back to the full original configuration. And so that's supposed to go right in here. Yeah, and it barely goes in. Clack. Alright, so it should be back to its original self. We'll see. I don't see it oscillating at all. No, because I'm not hooked up to it anymore. So I would see it blinking.
Do we need that 28 volt output on?
Yes, actually. So it's blinking. So
Yeah.
it's good. And then if it reads tape, it means it got the 4 kilohertz. It does, it got the 4 kilohertz, it read the stuff, and so now that scope is not hooked up to anything anymore, so I need to look at that one and see if it gives me PSK. It does! Repaired.
Nice.
Okay, well, the PSK box doesn't need any help from outside anymore. It's all good on its own without any keysight instruments. Very good. Had been a long time.